Okay, perfect. So I would like to present you a little bit about our RISC-V instruction set Explorer. That's a tool developed by my colleague and friend Nico and me. So I focus most of my research on ASIC design and RISC-V design, while Nico focuses most of his research time on implementing simulators. And at some point we decided that we could combine both of that to ease the design space exploration of the RISC-V world. Because due to the high amount of combinations that can be achieved through the high amount of extensions that are available from RISC-V, starting with decisions what base instruction set you're supposed to use, the integer one, the embedded one, 32-bit, 64-bit, then continuing with decisions on what of the extensions you're going to use, with the increasing number of extensions that are coming more and more. I didn't put all of them there because at some point it was too much work. But as you can see, the number of extensions is increasing significantly and making it harder and harder to find the right match for your application. So what we try to do is develop a tool that helps you answer several questions, like what basis do you start with, what extensions are you going to use, is your processor a little bit too big for the additional extensions, and how you actually implement your processor. And we want to support you with that using some high-level exploration tool. So what we try to do is we implemented an in-house simulator that implements additional profiling for analyzing floating point evaluations, your extension utilization, and more. Using a compiler environment, you feed in your executables, simulate the binary, get all the profiling results that you need from it, which can be shown in a graphical user interface. And then we also implemented automatic RISC-V customization, using the profiling results to suggest you instruction combinations that reduce the instruction or cycle count needed for your application. So what we try to achieve in that case is you just have to feed in your C code, and what it gets out is custom instructions, what extensions you're supposed to use, and in the end you just have to implement it. And of course we could combine it with other tools that would automate that as well, but up to now we are at that point. Maybe I can show you a little bit about that using our tools. So I'm currently connected to one of the Raspberry Pis that we have laying around in Aachen, running our simulators and others. One of the tools, for example, that we implemented are the QEMU. We, in the beginning, thought about using QEMU to do the profiling and simulate our results, but we wanted a faster solution and some more flexibility when implementing our profiling. So comparing our simulator with the QEMU implementation, you can see that we have a significant speed up, for example, for the whetstone benchmark. For example, for one of the benchmarks, we are able to achieve a speed up of factor of 3 compared to QEMU. And then we were able to get additional profiling results. For example, the execution of different basic blocks. Those are just the start addresses of the basic blocks, showing you how often any of the basic blocks are executed. We had additional values that include specific utilization of the floating point. So for each of the instructions that runs during your execution, you can see how often certain rounding modes are used, so whether you actually have to implement them, how often you have some nans or qnans, and information like that all gathered together here. Of course, it's not that easy to read in JSON files. That's why we also implemented a graphical user interface that I will show to you in a few minutes. Additionally, we also get automatically generated suggestions for custom instructions that also tell you then in that case what the speed up would be. In that case, you would, for example, for a simple instruction, have a speed up of a cycle reduction of 1%. We have some instructions that go to 4%. We are currently improving the automatic generation, but that's our current proof of concept. We are currently testing our new modes to improve the automatic customization. But maybe to show you a little bit more in our graphical user interface, you would just feed in your application, set some settings, start our tool, and then get your results immediately presented here to analyze the utilization of your processor. In that case, you can see, for example, that you have a high amount of utilization of the double precision instructions, additionally for the integer and the CSR registers. As you can see, none of the floating points are, for example, used. You can go a little bit more into depth, looking at specific instructions. For example, the floating point instructions, you can check how often they are actually executed, zooming in, having a look, so that you know what you actually need for your applications. So you just compile it for the instruction set that you need and analyze the results coming out. Pretty simple to get as fast as possible the evaluation to know what RISC-V processor suits your application. Additionally, also for the floating point evaluation, you can see where the values for your evaluation actually lie, whether you need 32-bit floating point or whether you actually need double precision for your computations. Additionally, we are currently implementing we implemented a register analysis to get some more information about the integer value utilization and about the memory bandwidth, but we didn't manage to connect it to the graphical user interface yet, and showing you another JSON file is not that interesting, but it's already there and implemented. And then for the custom instructions, you can then, for example, see it gives you immediate suggestion for your custom instruction, saving with that one, for example, about 4% of the instruction count. Okay, that would be it for me. I think I have maybe 1 or 2 minutes left. If there is a question, I can maybe answer one of them. And afterwards, I will still be available if you want to talk about anything from that. Thank you. So maybe one question?
Thank you. Yeah. Anyone? Others?
Okay.
There's one question. Yes.
Can you please explain, in your graphs, you were saying that with your graphs you can figure out when you need a floating point computation or not, depending on your algorithm. Can you please explain how you can figure out of that thing?
Okay, in that case, you have the minimum and maximum values for 64-bit double precision listed. The blue values, or the blue lines you can see here, are for your evaluation, actually what values you needed. As you can see here, for the maximum values, you're actually not going over the 32-bit line for floating point. For the minimum one, you go below it, but as those values kind of reach 0, you can think about whether you are actually cutting them off and going for a more sparse evaluation for your application. If you need those values, of course, you need to think about it. But it is, for example, in the field of neural networks, you can think about just using more sparse values and only using 32-bit, depending on what you want to compute.
Yeah, we can do it. One more.
You said it.
Maybe you say it loud enough and I repeat the question.
You said in the beginning that you want to explore or help explore which extensions are useful for you. So do you compile for different extensions for ZC extensions and so on to see the benefits for each extension?
We thought about in the beginning about automizing, compiling for different instruction sets so that you get all the evaluations get together. But it's kind of like exponential growth and how many compilations you actually have to do. We are currently working on doing a prior static analysis to reduce that evaluation space and continue that evaluation to kind of automate the whole process and just pop you out the final RISC-V configuration that's perfect for your case. Okay, thank you very much.
Thank
that
you.
would be it from me. If you have any questions later on, I will be walking around somewhere.